This hula hoop represents the horizon. If I bring it up to eye level and bend it just a teeny tiny bit, look what happens in the back. This is what happens if you see a curved horizon.
That's my daughter.
So, how do you know if the horizon is at eye level?
We can determine that using 1-point perspective. Let me show you.
1-point perspective like in a room drawing?
Yep, take a look. This is at eye level when I'm on my knees. And if I look up, because I'm looking at this door in front of me here, and there's more hallway on the other side of this door. But it's really cool because if I put this right at eye level, you can see the lines in the ceiling there. They all point right to the eye. And if I raise up, okay, I'm gonna put my nose right at eye level. Okay, and yeah, this is eye level. And the lines in the ceiling go right towards that spot. Let's see if I can do this.
So, why do you have to scoot back so far?
It's so you can see the lines in the ceiling still point to it from way back here. I'll show you in a second.
But you can barely see that. It's so tiny.
Let's try to focus on the eye height. You can still kind of see the general location where it was on the door, right?
Yeah.
Okay, focus on that. I'll show you in a second when I get to the end of this hall. There we go. See that? You got all of the lines on the ceiling and even on the floor. They're all pointing to that exact spot. They're that eye height. Can you see it?
Yeah.
You can't quite see it, but you can see that that's where I put the thing on the door, right?
How does that work?
That's 1-point perspective for you. It's kind of this weird thing. The vanishing point is going to be right at your eye level. Okay, now I'm going to do it again from the kneeling position. Check this out. So the camera's down low now, and you can see that all of the lines are pointing to a lower spot on the door, right where that paper was. You see that?
Uh-huh. Like, why do you have to scoot back so far? Can't you just do it up close?
You have to scoot back so you can see the lines on the ceiling. If you're right up close, you can't really see the lines on the ceiling. Now let's go take a look at some pictures of the horizon. Think you could do some 1-point perspective on that? Get a good vanishing point?
What's a vanishing point?
The vanishing point is that spot in the center that all the lines go to. See how the lines in the dock go to that one spot in the middle?
Yeah.
That's your vanishing point. Now here's another one, and I don't even have to really highlight the lines on this one in order to see that they all just kind of go right to the middle, right?
Yeah.
So we can use that to show that the horizon is at eye level. It's not always the case though, because sometimes the clouds in the distance will cover it up.
Like in this picture? It's so foggy that you can't really see it.
Yep. If I highlight this for you, you'll notice the same thing going on here. See how the vanishing point is going above the clouds here?
Yeah, I can see how the clouds are covering it up. So, what if the clouds on the left side are closer to you than on the right side?
Then you're going to get an uneven looking horizon like this. Now I've got to let Rob Skiba explain the significance of an eye-level horizon.
So if we imagine, let's call him PJ for short, if we imagine him standing on the beach ball, immediately the ball is curving downward and away from his feet in all directions. That's what a ball does. And it doesn't matter how big the person is, nor does it matter how big the ball is. But let's go ahead and shrink PJ and enlarge the ball for the sake of example here. Now, notice the lines are still curving downward and away in all directions, even though he's getting smaller and the ball is getting bigger. This never changes with scale. Okay, now let's zoom into tiny PJ on the massive ball here. PJ's clone walks 1 mile away. The top of his head would be 8 inches lower than PJ's. Another clone walks an additional mile, and the top of his head is then 32 inches below PJ's. The third clone walks one more mile, and at just 3 miles away from PJ, the ground clone number 3 is standing on is 6 feet below PJ's.
Alright, can you see this? How the horizon should never ever rise up to eye level if you're standing on a ball.
That's interesting.
Clone number 3's head is going to be even with the bottom of PJ's feet. Now, I'm not trying to see whether or not the person can see the other person. The ground level is the issue that I'm focused on with this example. Because if clone number 3's ground is 72 inches below the ground that PJ's standing on, it's going to be physically impossible for PJ to look straight ahead or to the left or the right or behind him and expect to see the horizon at his eye level.
That's because the horizon would be down and away from you if the Earth was a ball.
The blue circle at the top of the beach ball here, that's the visible horizon. So from whatever point you're standing on, in 360 degrees, that line is going to be the same. But that only works if you're looking down. I don't care how big the ball is. I don't care how small you are compared to the ball. If you're standing on the ball, from that point outward is receding downward at an exponential rate, which means you can never look out to this mystical circle out in front of you at eye level. It can't happen. While in principle, it sounds good, looks good, it does not exist in the observable, testable, and repeatable example of reality. According to Pythagorean math, the 25,000-mile circumference ball Eratosthenes invented does not allow for us to ever be able to see the supposed edge of a horizon that presents itself at eye level.
This is the horizon at sea level. This is the horizon at 1,200 feet. And this is the horizon at 5,600 feet. So yeah, the horizon drops with altitude. Yet another way to show we live on a globe. Thanks, Kyle.
In what way does an eye-level horizon show me that we live on a globe? Niles has chosen not to answer. Okay, what are your thoughts about all of this? Do you think that's showing that we live on a globe?
No, I don't think that has much proof, at all.
Why not?
Well, I don't know. It just doesn't make sense.
Okay, please notice how the very first picture he showed us at sea level is showing us the horizon at eye level. And then the rest of everything else is trying to distract you from that. Do you see that?
Yeah.
He's trying to change the topic there.
What is he even trying to change the topic to?
He's trying to change the topic to instances where you don't see the horizon at eye level. When you do see the horizon at eye level, it's a major problem for the globe Earth. He's trying to say, look away, look away! Rather than trying to explain that on the globe Earth, he's trying to say, yeah, well, try and explain this on the flat Earth and how it can go below eye level.
Okay, so how do you explain that?
His tactic appears to be working. Do you remember our foggy horizon example here?
Yeah.
Do you notice something in common with those two bottom pictures there? The horizons in both of those pictures are really cloudy. Do you see that?
Uh-huh. Picture on the bottom right isn't even a straight horizon.
That's because of the clouds. Niles, do you agree that the horizon appears to change position because of the weather? Niles has chosen not to answer.
Come on.
I agree. Weather can limit our range of vision.
That's not quite what I asked, but thank you.
Do you agree that if you see curvature in front of you at eye level, the horizon won't be eye level all the way around you?
Okay, I agree with this.
This message has been brought to you by the Flat Earth Institute of Science.
With a shout out to our Flat Earth friends at jdecals.com. Hold it up, hold it up, hold it up.
Can you take a video and I'll say the Earth is
You gotta, whoa, 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 both of them.
The Earth is flat! The Earth is
All right,
flat!
come over here, come over here. Come over here in the street. I love it.